All right, let's jump right into this explainer. Today, we're exploring a truly fascinating intersection, the exact point where theoretical gravity meets quantum mechanics. We're going to unpack some concepts from a high-level physics group meeting, and I've got to warn you, the ideas we're about to cover are absolutely mind-bending. We are literally looking at how the physical geometry of space-time talks directly to quantum entanglement. There's this really profound quote from our source material that perfectly captures the core mystery we're trying to solve today. It says that general relativity, Einstein's monumental theory of gravity and curved space-time, appears to possess this deep, inherent understanding of quantum information. When physicists push the absolute limits of these theories, studying what we call semiclassical gravity, they just keep finding that the math points directly to quantum quantities. It's kind of like these two completely different languages of physics are secretly translating each other behind the scenes. So, let's get into Section 1, Merging Two Worlds, Building a Connection Between Physical Space and Quantum States. To really grasp this, we first need to understand the playing field. We're essentially merging two distinct arenas here. First, we have what physicists call the bulk. Think of the bulk as the 3D interior of a snow globe. It's where physical objects crash into each other and where gravity operates. That's the domain of general relativity. On the flip side, we have the boundary. Imagine this as the 2D glass surface of that snow globe. It's this lower dimensional realm governed entirely by quantum information, where we look at entanglement and surface information protocols. Our main goal today is to figure out exactly how an event happening deep inside that bulk translates to quantum signatures out on the boundary. That brings us to Section 2, the connected wedge theorem. This is all about how internal actions force external connections. And this revolves around Alex May's groundbreaking 2019 connected wedge theorem. The theorem proposes something that's honestly incredible. It says that if a holographic scattering event happens deep inside the bulk, it physically demands that there be a connected entanglement wedge out on the boundary. Basically, this brilliantly illustrates that a physical event deep inside a space requires a measurable quantum connection on its outside surface. You simply cannot have objects interacting in the center of the universe without the outer edges of that universe being quantumly entangled. So where did this idea even come from? Well, interestingly enough, it was actually inspired by quantum information protocols, specifically a concept related to quantum spoofing. In the quantum world, if you want to fake or spoof a local scattering process using only signals on the boundary, without anyone actually meeting in the middle, you can only pull that off if you possess a massive resource of quantum entanglement. Alex May looked at this and asked, if holography is real and bulk scattering equals a boundary process, what is that demand of the boundary itself? And the answer, it turns out, is entanglement. Moving right along to Section 3, Scattering and Entanglement, visualizing the geometry of the theorem. To really get a grip on this, we need to map out the physical geometry of a 2-to-2 scattering process. Imagine looking at our universe like it's a giant cylinder. First, we take two input points on the outer boundary, C1 and C2, and they send light signals inward into the bulk. Then, these light signals travel into the past and future light cones, eventually meeting and scattering off one another deep inside the bulk space. Finally, the resulting output signals travel back outward, hitting two completely different points on the boundary, R1 and R2. And what this does is create a distinct, closed causal region right in the middle of the bulk. Now, here is the wild part. If this causal scattering process successfully happens inside, it forces a strict condition on the outside. The crucial point is that simply having bulk scattering guarantees a massive amount of mutual information, or entanglement, between the distant boundary regions associated with those inputs. Specifically, the mutual information must be strictly greater than 0. In fact, it's at the semiclassical order of 1 over Newton's constant. So, what does that mean in plain English? It means the physical crash inside guarantees a truly massive macroscopic amount of quantum entanglement on the outside. The physical reality of the internal crash ensures a measurable quantum link between those isolated surface areas. The source actually uses a brilliant comparison here, likening this geometry to nested Russian matryoshka dolls, and it really is the perfect way to picture it. When you map it all out, you get 3 nested regions. Safely tucked right in the center is the innermost scattering region where the points actually meet. Surrounding that are the entanglement wedges of the specific boundary areas. And surrounding all of that is the outermost intersection of the connected wedges. So the scattering region lives safely nested inside these much larger quantum boundaries, fundamentally linking their geometries together. All right, Section 4, Proving with Light Sheets, the mathematical engine behind the theorem. So now that we have our geometric regions visualized, a pretty massive question comes up. How in the world do physicists actually prove that this nested relationship bounds the entanglement? Well, they actually bypass getting bogged down in incredibly complex local quantum operators. Instead, they use a really clever shortcut. It's a purely geometric proof, and the answer lies in tracking the edges of these regions using something called light sheets. To pull this off, they rely on a really heavy-hitting piece of math called the Rachel-Jury equation. This is a formula demonstrating that the expansion of light sheets, or null congruences, must decrease, or focus, as they travel away from specific extremal surfaces. Think of it like the beam of a flashlight, narrowing down to a sharp, focused point as it travels. Because of the energy conditions in general relativity, when you shoot these light sheets out, their expansion is negative. So this equation acts as our mathematical engine, mathematically guaranteeing that as light sheets are shot outward, their cross-sectional areas naturally shrink and focus to form boundaries, or what the physicist in the source refers to as ridges. Here's how that proof actually plays out in practice. First, physicists shoot these light sheets outward from the ridges of the nested regions we just talked about. Then, using that Rayleigh-Jury equation, they track the focusing of the light to prove mathematically that the area continuously decreases. Finally, they compare these shrunken, focused areas to the geodesics on the boundary. By meticulously tracking these shrinking areas up and back down, they establish a firm mathematical bound, and that proves the mutual information requirement entirely through the action and geometry of spacetime itself. It's honestly beautiful. Which brings us to Section 5, the future of holography, exploring the converse and advanced entanglement. Okay, so we've seen that scattering implies entanglement, but what about the reverse? Can we safely say that overlapping entanglement guarantees scattering? To explore this converse idea, physicists need incredibly precise definitions. Notice how Raphael Bousso introduced these max and min wedges to precisely handle complex scenarios. The max entanglement wedge is the largest bulk region reconstructible from a boundary, while the min wedge is the smallest region outside of which no operators can be constructed. Now, when you're dealing with pure, perfectly known quantum states, these wedges are often exactly the same, but with messy, complicated mixed states, they diverge. These advanced definitions really do the heavy lifting in the math. By using quantum focusing, these max and min wedges provide a rigorous lower and upper mathematical bound for the entropy of a bulk scattering region. They allow physicists to construct precise holographic regions that test the exact limits of the connected wedge theorem, pushing our understanding of how quantum information restricts the literal physical shape of gravity. Of course, a lot of this work is done in theoretical, curved spaces, like anti-de Sitter space. But the ultimate goal discussed in this source is taking flat limits to apply this to our own flat universe. So, what does this geometric mapping tell us when we try to connect it to actual scattering out there in the real world? Ultimately, this incredible alignment between the geometric focusing of light in general relativity and the mutual information bounds of quantum mechanics leaves us with one massive question. What other profound secrets are hiding in the geometry of our universe? Thanks so much for joining me on this explainer. Keep wondering, keep exploring, and I'll catch you on the next one.